Hello, we are Group 9, Predictable Control of Spatial Patterns. Our project is based on the previous work of PhD student Anita Silver on the growth of pseudomonas colonies under different conditions. Our goal was to be able to predict this growth, and this prediction is possible with mechanistic models, but this is incredibly time-consuming and just inefficient. So our work has centered on using a neural net, specifically a U-net, to generate images from the parameters inputted. And on the top here, you see some outputs from the mechanistic model, and on the bottom, you see outputs from our U-net trained model. And an important area of this image generation is the tuning of hyperparameters that compose the net. So for that, we used Optuna to automate our hyperparameter search, as well as ease our parallelization efforts.
Our project has three main sources of data: experimental results, mechanistic model outputs, and neural net outputs. Since the mechanistic and neural net models generate datasets directly, they were designed to store this information in a way that's convenient for later analysis. The results from the wet lab experiments are recorded as a series of images, where each image corresponds to specific input parameters. To make this experimental data easily accessible for analysis and comparison to the data from the other models, we created and implemented a custom PyTorch dataset to store this information as two vectors, as you can see on the right. Our goal in creating the experimental dataset was to have a convenient way to access the metadata, such as agar and nutrient density values, for each image. This dataset lets us easily test loss functions and evaluation metrics on the experimental data, which can help us determine which methods may work best for the neural net.
So these are two images of identical parameter inputs. These are experimental images. And what you see is you get an intuitive sense that these images are similar, but there's kind of some inherent randomness in experiments that makes their individual pixels different. So if you're looking at a loss function, something that's just comparing pixel to pixel is really losing part of the picture. So when looking for ways to categorize the shape of things that's independent of like local distortions, translations, or rotations, kind of a natural conclusion is to use some sort of topological analysis. And this is not a new idea in image processing. Here you can see a downstream pipeline being trained to have one larger connected component as opposed to several smaller non-connected components. And I worked throughout the summer to try and generalize some form of a topological feature or extraction or information about these images. And so far it's been unsuccessful in putting these into a machine learning pipeline, but that's kind of the future work of the project, is to categorize shapes as topological features and then create a model that can generate images based off of that.